Training in Weld Quality Assurance and Quality Control. Section 4, Discontinuities and Defects. Topic 3, the common causes of discontinuities related to shape, size, and contour. The objective of this topic is to be able to identify the common causes of weld discontinuities and to be able to determine the cause as related to the joint welding procedure. In order for welding inspectors to perform their duties effectively, the causes of weld or weldment discontinuities must be clearly understood. The reason for this is that knowledge of the causes permits quality control personnel to determine where further or earlier inspection should be performed in order to assure that procedures are being properly followed. One of the primary jobs of a welding inspector is to inspect the weldment and assure that it meets the requirements of the design. To do this, the inspector must be familiar with the standards which spell out the acceptable limits for weld discontinuities and must also be familiar with the weld procedure that pertains to the particular weldment. Defects such as excessive weld reinforcement, incorrect weld size, incorrect profile, and incorrect final weldment dimensions will be discussed in this topic. Excessive weld reinforcement is a discontinuity in which extra weld metal has been deposited in the joint, either at the root or face, forming a highly convex contour. Excessive reinforcement is an economic waste and is also objectionable in appearance. The most common causes of excessive reinforcement are poor joint fit-up, incorrect welding technique, incorrect welding current settings, and improper selection of filler materials or electrodes. In the case of poor fit-up, a root opening which is too wide or a root face that is too small will contribute to excessive reinforcement. In both cases, the weld may be unacceptable if the penetration or root reinforcement is more than specified. Poor welding technique, such as wrong electrode angles or slow travel speed, may cause excessive reinforcement. Traveling too slowly adds more weld metal to the puddle than necessary. Incorrect work and travel angles may improperly direct the filler metal and may also cause the weld deposit to pile up and droop. Another example of improper technique is the improper sequencing of weld beads. By locating beads improperly within layers or depositing too many layers in a joint, the face may become excessively reinforced or inconsistent. If current settings are too high, excess weld metal may also be deposited. Another contributing factor is the use of an electrode or filler metal that is too large for the joint design or base metal thickness. The larger the filler, the more weld metal will be deposited. When inspection reveals a weld with excessive reinforcement, determine the cause by reviewing the requirements in the welding procedure. Variables in the procedure should all be checked, such as weld sequencing, amperage and voltage settings, fit-up, and the type and size of electrode. It is possible that the welding procedure is not suitable for the type of weld required, or the welder may not have the ability to weld to the requirements of the procedure. In either case, it may be necessary to requalify the procedure or to requalify the welder to the procedure. Excessive reinforcement can be prevented if the procedure is followed and the welder can demonstrate the ability to weld in accordance with the procedure. Another common discontinuity that can lead to weld failure are welds that are incorrect in size. When working to codes and standards, tolerances can be very precise. The amount of precision is based on the code and the design of the particular weldment. Complete welding information should be provided on the engineering drawings through the correct use of welding symbols. Welds that are not the correct size may be detected visually with the use of gauges designed for this purpose, or by comparison with approved workmanship samples. Incorrect weld size is considered a defect, since too small a weld may not support the weldment in service, and welds which are too large might also cause a weldment to fail. In general, the larger the weld, the stronger it is expected to be, but this is true only within sound engineering principles. When a weld is too large for the joint design, more heat and residual stress is present, which can lead to weldment failure. Excessive welding is also wasteful and time-consuming and may be objectionable in appearance. The most common cause for size-related discontinuities is simply a lack of communication to the welder. Incomplete or missing size information on engineering drawings or joint details results in welds of various sizes based on decisions made by the welder. As a result, the weld itself may be sound and have good appearance, but can be rejected because it is the wrong size. A contributing cause might be the use of an incorrect welding process or electrode. Again, a lack of communication. If the welder or operator understands the information presented on blueprints, drawings, or procedures, many weld failure errors can be eliminated. Essentially, the key for prevention of incorrect weld size is to assure that the welder or operator is informed of all requirements pertaining to the weld. The next type of discontinuity related to shape, size, and contour are welds with incorrect profile. Discontinuities falling under this category are undercut, overlap, and underfill. All of these discontinuities can alter the strength and appearance of a weld. Undercut is an unfilled groove that is melted into the base metal adjacent to the toe or the root of the weld. Undercutting damages a weld because it reduces the cross-sectional area and may introduce stress concentrations. Undercutting may be caused by poor torch, gun, or electrode control, using the wrong work or travel angles, applying too much welding heat or current, or by using the wrong travel speeds. Many welding processes require the arc and filler metal to be manipulated during welding. If such manipulations are not consistent and controlled, undercutting of the joint is possible. Also, if work and travel angles are held incorrectly, the filler metal will be deposited too high or low in the joint, creating undercut along one of the toes. When welding current is set too high, more heat is applied, and the puddle may become too large and wash the side away, creating undercut. In the horizontal position, a slow travel speed will cause the weld metal to droop down from the upper toe to the center of the puddle, leaving undercuts along the upper toe. Too fast a travel speed, on the other hand, may not allow the weld metal to flow out into the base metal before it freezes. When undercut is present in a weld, the variables of the welding procedure should be checked to determine if the requirements of the weld are being followed. The most common ones to check are welding current, voltage, bead sequence, and travel speed. The second profile discontinuity to be discussed is overlap, the bulging or protruding portion of a weld that extends beyond the toe, face, or root. Overlap can occur on both fillet and groove welds. On fillet welds, overlap reduces the actual size of the weld and creates stress concentrations along the toes, reducing strength. On groove welds, stress concentrations are produced at the toe that can cause toe cracks in service. Overlap can be produced when the weld puddle is too large and becomes difficult to control, flowing ahead of the arc. This is common when welding out of position. Improper cleaning of base metal surfaces can also cause overlap, especially when oxides cover the surface and prevent the weld metal from fusing with the surface. Failure to remove mill scale or other surface coatings such as paint and oil will prevent the molten metal from fusing properly. The single most common cause of overlap is an excessively large weld puddle which can flow ahead of the arc. The third common profile discontinuity to be discussed is underfill, the lack of sufficient weld metal at the face or the root. In multiple pass welds, an improper sequencing of weld beads will prevent the joint from filling properly, resulting in an underfilled face. On fillet welds, the face will be excessively concave, resulting in a reduction of the throat area of the weld below the designated size. This creates weak points and potential failure. Underfill may also be present on groove welds on either the face or the root side. On pipe welds, underfill is most common at the root and is referred to as internal root concavity or as suckback. When welding in the overhead position, a root opening that is too wide or too hot a joint will cause the puddle to sag in and become concave during solidification. The face of a weld can become concave when too wide of an oscillation is being used. This occurs when an overly large puddle is created in an attempt to deposit a relatively large or wide weld. If underfill is a problem, the welding procedure should be reviewed in order to assure that the proper joint fit-up, weld sequencing, and other variables that prevent underfill are being followed. The final discontinuity to be discussed in this topic relates to incorrect final weldment dimensions. This type of discontinuity is directly related to distortion and warpage. Most of the welding processes involve heat, and it's these high temperatures that are largely responsible for welding distortion, warpage, and internal stresses. When metal is heated, it expands in all directions. And when it cools, it contracts in all directions. It is the non-uniform heating and cooling of a weldment and the partial restraint resulting from the parts that cause distortion and warpage to occur. Shrinkage of the weld during cooling can cause various types of distortion and dimensional changes. If this is to be minimized or prevented, strategies must be used to overcome the effects of the heating and cooling cycles of the weld. This should be done both in the design stage and in the shop during fabrication. One strategy is to keep the shrinkage forces as low as possible by depositing only the amount of weld metal that is required by the procedure and indicated on the drawings. Do not over-weld. Understanding the amount of heat input for a given weld length will also aid in devising strategies. The total heat input must be balanced to produce the desired weld. It is estimated that the temperature of the molten steel in the puddle is about 3,500 degrees Fahrenheit. Extra heat is required over and above the amount needed to melt the filler metal and the base metal surface in order to compensate for the heat that is conducted away from the weld. It is necessary, therefore, to closely control the amount of heat input while welding. Heat input can be calculated by multiplying the voltage and amperage levels by 60 and dividing by the travel speed, which gives a measurement in joules per inch of weld. Proper edge preparation and fit-up can also minimize the required amount of weld metal and in turn control distortion. And by making shrinkage forces work in a desired direction, such as presetting the parts will be pulled back into proper alignment by the same forces that would have ordinarily distorted the weldment. One widely used means of controlling distortion is by the use of clamps and fixtures that hold and rigidly lock the parts in place during and after welding. Another way to control heat input is through the careful sequencing of weld beads, alternating sides at given intervals to balance the heat on both sides of the weldment. The same effect can be accomplished by intermittent welds, rather than continuous welds, where the design permits. A backstepping technique may also be employed in which segments of the weld are deposited in the opposite direction of the progress along the joint. This and a variety of other sequencing techniques have the effect of balancing the heat input, thereby decreasing distortion effects. In summary, it is important that all conditions leading to welding defects are understood with reference to the welding procedure. This includes conditions before welding, such as ensuring the use of correct materials and making sure that the parts are prepared and aligned according to the joint detail of the welding procedure. Conditions during welding should also be monitored to reduce the chances of discontinuities forming during fabrication of the weldment. Finally, post-welding conditions must be understood and followed to ensure the overall acceptance of the weldment. Many weld or weldment failures can be eliminated if conditions are carefully controlled during all phases of fabrication.